Two main topics for today are to go through as much of these slides as we can manage, as well as an introduction to Emacs. It's not required to use Emacs. You can use any editor. It's nice to have one that can balance parentheses and do automatic indentation. But even if you're using a different editor for your main editing, at least at the beginning, I think it's still advantageous to learn this REPL, or read, eval, print loop, the command line in Emacs. If you can use that much in Emacs, then you can still get much of the benefit of the Emacs integration without having to make the full dive into Emacs as your editor. But what I'll be presenting here will use Emacs as the full editor. The command line is a basic Lisp command line, so you can say things like list 1, 2, and see the return value. It's reading what you type, it's evaluating it, and then printing the result. REPL, or REPL. And it even says REPL down here. Let's start the Emacs tutorial. And you can always do that under the help menu of Emacs. There's the Emacs tutorial. This is worth doing if you want to try using Emacs as your editor, which I resisted. Years ago, I was a VI guy, and then eventually we realized that Emacs has a lot of nice things that have built in over decades for editing not only Lisp programs, but for a lot of the things that you want to do. Emacs is what they call a keycord-based editor. So you use a lot of control and meta, and for that purpose, it can be very handy. I always have my machines customized so that the caps lock is mapped to a control key, and then the meta key is usually automatically bound to the Alt. Of course, the mouse works too. You can simply point the mouse to move around. But once you get these key chords in your finger memory, they tend to be quicker. With the notation they use, a capital C dash and then some character means hold the control while typing that character. So Control F, which I'm doing right now, is hold the control, press F, and that moves forward one character. So that's one way to move the point around. So to end the Emacs session, Control X, Control C. We won't do that right now. This Control G is very important because sometimes you'll get halfway through an Emacs command and want to back out. And Control G will always quit whatever you've started doing and get back to a neutral state. And you see the quit down in the, what's called the mini buffer, the feedback area at the bottom of the screen. So now we'll go through the directions that they tell us in the tutorial, and you can repeat these on your own probably very quickly after seeing them here. So it's saying type Control V to view the next screen to move to the next screen. So Control and V, and now we've paged down by one screen. Now if your keyboard has page down keys, those will work as well. Especially if you're a touch typist, after you use these a few times, you find out you don't have to look at the keyboard, you don't have to move your hands. So Control V is move forward one screen full, we'll do that again, but then Meta V moves back. So I've just gone forward a screen and now back a screen. And then Control L will redisplay the text and it will also center you on the screen. So Control L actually cycles through. Now my point is down at the bottom of the screen, you can see it there. If I do Control L again, I've centered the point. And then Control L again, and my point is at the top of the screen. Wherever your point is, it's often that you'll want to center that on the screen, so that a single Control L will do that. So of course you can use arrow keys, you can use a mouse, but as they say here, it's more efficient to keep your hands in the standard position. So Control P for previous, that's previous line. Control F is forward to character. Control N is next, it means next line, and Control B is backward. So those are the four directions on the screen, and it's summarized for you right here. This lesson today is going to flip back and forth between Common Lisp and Emacs. If we're already at the beginning of a line, Control B goes up. So it moves back actually across the new line character is what's happening. So text will scroll if you go off the ends of the screen with these. So if we go Control N off the end of the screen, it scrolls up. The next level is with meta. Instead of control, we use these same keys, but with meta, we'll go forward by larger units, namely one word at a time. So meta F brings me forward by a word, meta B brings me back by a word. And oftentimes this kind of pattern is repeated where a meta will do something on a bigger scale than a control. So now Control A, Control E. Right? We don't use those meta A, meta E much, but that's good to know. So Control E brings us to the end of the line, Control A to the beginning of the line. Meta A, beginning of a sentence. Meta E goes to the end of the current sentence. Here's a summary. Try some of these for practice. So two other commands for moving the cursor around. Meta less than, meta greater than. Usually you need shift for the greater than and less than. So now they want us to move all the way to the beginning of the tutorial, then we'll use Control V, which is page down, to get back to where we were. So usually the finger memory for this is shift and meta with the left hand. I wish we could have a picture of the keyboard and the fingers right now, would be helpful. Shift and meta with the left hand, small finger and thumb of the left hand. And then with the right hand, the less than sign. So that brings us to the beginning. And now Control V brings us back down a page at a time to where we were. So the arrow keys will work, but they give reasons for just going ahead and learning these control characters. The numeric prefix works in a lot of places. So that's with Control U. For example, you're debugging a program and something tells you that character number 500 has a problem in this program. So we go Control U, 500, Control F, and that jumps us forward by 500 characters. This Control G, they repeat the importance of that here. If Emacs stops responding, it usually you've started some command and the command becomes non-responsive for some reason. Control G will almost always bring you out of it. It makes a little beep too. So now we get into the windows, the idea of windows. That's where we'll start to bring in the read eval print loop of Common Lisp. When they talk about windows, they're tiled windows. Control X1 makes the current window the only window. It's not closing those files or you're not losing any work. It's just closing the display of those other windows. Control X2 to split it horizontally this way. With most people these days having widescreen ratios, sometimes it's more useful to split vertically, and that's Control X3. So we get two side-by-side tiles, and that's what we'll use for right now. Let's go ahead with our other window on the side here. And the buffer menu shows us we have a Slime read eval print loop, a few different ones running, because Slime actually lets you attach to as many Lisp sessions as you want. But we'll go to this first one, which is a ANSI mode Allegro CL based one. Even if you're using the Franz IDE, I would still recommend using this REPL for doing certain commands. Run a little small Emacs window side by side with the Franz IDE so that you can just benefit from all the same standard commands in the REPL. 90% of the heavy lifting, it really is learning just these basics of moving around in Emacs. And then the Slime things are some natural extensions on top of that. And then the Glime things is additional feedback, GDL specific feedback that you're getting on top of that. So to insert text, not like some editors like VI, you have to go in a special mode to insert. Emacs, the default mode is always insertion. So whenever you type, you're inserting text. Let's do it over here at the REPL instead, because these same things apply at the REPL. And then we'll transition over to the slides. So this is a bit outdated. This is approaching more like 18 years now, running GenWorks. We've been providing the GDL product since 2002. Prior to that, I was from the beginning of 93 to the end of 97. So it's pretty much 5 years at Ford doing ICAD applications. I had learned Lisp in artificial intelligence courses at university. Educational background, bachelor and master in computer science at Michigan, and I had some work in both the database industry and the CAD industry before my master's degree. So I have a few different perspectives coming into these things that I think the KBE is sort of a hybrid of all these things. Lisp as a concept is slightly younger than Fortran, and so it's considered the second oldest high-level language still in use. In many ways, still on the leading edge. The main thing is that it really was designed right from the beginning, and especially Common Lisp with the Common Lisp object system, was designed to evolve, to be really adaptable. Lisp, which is a different variant than Common Lisp, but it's a Emacs Lisp. And then, of course, the ICAD system, it's still survives in little niches and corners in the world. AutoCAD has its own Lisp variant. A lot of game development has happened with Lisp. Window Manager for Linux, that's seen a lot of popularity lately, is based on, I think, Common Lisp itself. It's called Sawfish. I just saw an ad. They're hiring Common Lispers at Roomba, iRobot, that make the vacuum robots. Apparently Common Lisp is running those things, or is used to develop on them anyway. So it's really the original rapid application development. Can write a prototype faster than you can really write a paper spec, and the prototype is a better spec than an actual spec. That's, of course, controversial in a lot of IT departments and corporate ways of doing things. There's a saying that Common Lisp is good for writing applications fast. It's also good for writing fast applications. And sometimes those two things happen in slightly different phases. So it's hard to specify something if you've never solved something like it before. So it's really nice to have a discovery, exploratory kind of environment to be able to help you understand what the problem is that you're trying to solve at the same time as you're moving ahead solving it, because you always discover new things that weren't specified at the beginning as you're going along. The syntax itself can be summarized really in a few slides, the so-called syntax. The source code itself is made up of S expressions, and these are lists, or they're atoms, where an atom is something like a number, a symbol, or a string. The list is delineated by parentheses. What's in blue is intended to be entered at a REPL, and what's in green is the return value that you would expect to see. These slides are actually generated live, and this session is running in ANSI mode, which is why the symbols that you see come back will be uppercased. So symbols, when they read into the system in ANSI mode, they convert to uppercase by default. There's also modern mode, which is available in Allegro Lisp and GDL and a few other Lisps. So if we look at the modern mode, you'll see these symbols coming back in lowercase because they were typed in lowercase. But we'll stay with the ANSI mode. GDL is written to work in either or equally. If you want to ever switch an application over to modern mode, there are a few rules of thumb. So we'll go ahead and copy-paste some of these things into the REPL just to see how it behaves. So this is a literal list starting with a single quote. It means don't evaluate anything inside, just come back with that literal list. Here's another, which is a nested list of lists, and so on. These are individual atoms. Point here is just to look at the shape of these. Look at what they look like. Convince yourself that each one is an S expression, because it's either a list or it's an atom. And if it's a list, then it can also contain lists. Syntax is prefix notation in terms of function calling. So if we enter an S expression without that quote at the beginning, then we're asking for it to evaluate the first item as a function name, and the rest are arguments to that function. Notice there are no additional parentheses around the arguments. It's just the function name and then the arguments. And that returns a 9. I've just used Control L to center ourselves after entering that. Now we'll learn a few more things about the REPL. Meta P will go back to previous commands. Usually after you've typed a few commands in a session, you'll be just doing different variations on those same commands. So meta P is a very useful thing to know. Meta P and then meta N goes back through. So right now I'm going meta P to go backward through what I've just entered, and then meta N for next. On most keyboards, when they say delete, it's backspace. If you want to delete things to the right of the cursor, it's Control D. Control D works like a delete key. And then Control A to the beginning of the line. So if we enter a command at the REPL, and then you want to kill that whole command to do something else, it's a matter of Control A to the beginning of the line, and then Control K deletes from the rest of that line. These same basic keys work in a lot of places that you may not expect as well, like in Chrome web browser and in Bash shells. Learning these keys can be useful for a lot of things. Killed text can be reinserted. If I kill that line, we can reinsert it with so-called yank. Yank is Emacs's jargon for paste. When we kill that line, we can yank it back with Control Y for yank. If we Control K several things, like I'll do this 2, 3, 5, kill that. I'll go up here and kill the 2, 3, 4. I'll kill this. Now, if I do Control Yank to bring back the most recently killed thing, I can get all the previously killed things with meta Y. That goes back through the whole, what they call the ring. So it keeps a ring all the way from as far back as your session goes of things that have been killed with Control K. Control Y would yank the most recent kill. Meta Y, if you type it enough times, it'll cycle all the way back to the first thing in that kill ring. To undo, I usually use Control X U. Control slash is also an undo. You can just keep typing Control slash and it'll repeatedly undo, I think pretty much infinitely. We have prefix notation, which means when you do have an operator, it always comes first, and then the arguments come next. If you have arguments which themselves are expressions, then the whole thing is recursive like that. One advantage is that there's no ambiguity in terms of the order of operations. You don't have to think to yourself, okay, multiply always comes before addition and subtraction and stuff like that. It's all very explicitly laid out. So that's about all there is to know in terms of syntax for Lisp. It's about as minimal as you can get. So no special cases, really no ambiguities. Well, there are some special forms, but they're not really special cases. Welcome relief from some languages with all the different characters that mean different surprising things. Symbols evaluate as variables. So if you have a symbol and you evaluate that at the top level, like a global symbol, like print length, which by default is nil, that will return nil. Now the stars around that symbol are just convention. Conventionally, global parameters or global variables have stars, just to identify them as globals. They're also usually known as special variables, which means they have a special kind of behavior at runtime. If you bind them locally and call a function, then that whole function call tree will have the bound value of that variable because it's declared globally. Other atoms, so other atoms include numbers, strings, keyword symbols, quoted symbols. They will all evaluate to themselves. So number 42 just comes back as a number 42. And those numbers can be floating point, real numbers, even ratios. If we put 42 over 2, it evaluates and comes back as 21. But if you have something that doesn't divide any farther, it actually stays as the ratio itself. That's why you may hear some people say that Lisp has infinite precision, which is true when you talk about ratios. For fractions, it has infinite precision. Because as long as you can carry that number as a fraction, you're not cutting off at some arbitrary floating point decimal value. Keyword symbols are symbols that start with a colon. They end up in a special package. But a lot of symbols do start with a colon. That means that they're pretty much used as a name. A symbol that doesn't start with a colon, you have to use a quote for it to be a literal symbol. Otherwise, it would try to evaluate that as a variable. So if we put quoted symbol A, it comes back as a A. If we try to evaluate A like this, we get an error. Attempt to take the value of the unbound variable A. Now in Slime, if you get an error, you just type A to get out of the error. A or Q. A is accept. I think it really means abort, but I think of it as accept. You've accepted the error and now we just move on. Or Q, quits, is another default way to quit out of the error. And later on we'll learn how to go into these different restarts and how to go into this backtrace to see what it was trying to do up to the point where it got that error. And you can check out local values of things and what they were when it was trying to evaluate and so on. But 9 times out of 10, when you get an error like this, in Slime it's called the SLDB. That's the slime debug buffer, number 1. You don't want to have too many of these open things. If you don't close this and you get another one, you can get these stacked up. So 9 times out of 10, when you see this, you look at it, you say, okay. Hopefully it's clear what the error is. Just type A, and that closes the error, pops up out of the error level, and you're back at the normal REPL. I suppose we could do something with files. Let's start to put some of these examples in a file in Emacs, just to make things a little bit cleaner. In order to make your text permanent, this is a buffer here. You can save this buffer if you want. If you want to save a history of your working session, you can always save the REPL, but by default, this isn't any physical file anywhere. It's just a temporary buffer where you're typing things and getting results. When you exit your session, this goes away. The fact that you have these stars here shows you that it's not saved anywhere. It's not a saved buffer. Notice the tutorial doesn't have any stars because it's the saved file, and I haven't modified it at all. If I start modifying it, then these asterisks show up. It tells me this is modified, it's not saved. I'll go ahead and undo what I just did. Now the asterisks go away because it's back to the state it was when it was saved. So let's use Control-X, Control-F to find a file. That's also under the File menu. Visit New File, Control-X, Control-F. Tells you the shortcut right there. But I'll go ahead and use the keyboard one. So Control-X, Control-F, and then in the mini buffer, it gives me a chance to look for files. And just for good measure, for a Lisp file, we usually put an in package at the beginning. So that's the default package that everything, when the Lisp reader reads this, that's the default package that all the symbols will be assumed to be relative to. The way symbols work needs a little understanding too, but we try to set things up so you don't have to think too hard about it. GDL user is a default package that gives you access to all the normal GDL functionality without having to specify symbol package prefixes. Packages being like area codes for your symbol. GDL user also has access to all the standard Common Lisp stuff as well. So if we put, the plus, that's part of the Common Lisp. And there are ways of looking up in case you don't know what package a symbol is coming from. There are ways of evaluating this stuff directly from the buffer, from this file with Slime. But for today, we'll just do things at the REPL. To select, you control space to begin a selection, and then whenever you move around, it'll highlight the selection. And then meta W copies whatever's highlighted. Control X O for other window, and then Control Y to yank what we've copied. That's one way to copy paste. Of course, you can do this stuff with the mouse. There is a mode for Emacs which makes it behave almost like a normal Windows editor with Control C copy, Control V paste, and using the mouse. But for Lisp expressions, Control Meta space selects the entire form. You put the point on the opening parentheses of an expression, and then hold down with your right hand Control and Meta and type space. That will select the whole form to the end, so you don't have to worry about finding the matching parenthesis at the end. And then Meta W copies that. Meta W always copies the selection. Again, Control X O jumps me to the other window, Control Y paste, and now we can test that expression here. So if the arguments themselves are expressions, then they're just evaluated recursively in that same manner. Get this one into play. So there's our answer for that one. And if you wanted to convince yourself, Meta P brings that back, Control A. Let's say I just want to check out that portion to see what that was. And now let's check out the other portion. So that's one way to sort of break down an expression and see what was going on. They're evaluated in order. If there were some side effect happening by this, then it would be seen by this. The ordering is guaranteed to be left to right. Many functions can have variable number of arguments. Wherever it makes sense, they're usually variable number of arguments. There's no repeating of the plus sign. You simply string along the arguments. Slime tells you the required arguments, if any. So list returned by quote may be assumed to be immutable. You should never modify them in place using any destructive operator. We'll talk about that a little more when we talk about destructive operators. But once you have a list like that, there's a function eval you could call to actually evaluate it. But 99% of the time, we don't use eval explicitly like this. If you have programs where it's actually using eval, that's usually a red flag that something can be done more elegantly and more properly. We don't usually call eval explicitly like that. The basic data types, numbers, strings like you're used to in other languages, and then these fundamental types, symbols and lists, are a little bit unique to Lisp, especially symbols. Other languages have sequence types, but symbols have a lot of depth in Lisp, especially Common Lisp, that you don't really see in other languages. They're pretty much interchangeable with strings in a lot of cases in other languages. But a symbol is an actual object. It's not simply a string, and it has a lot of things behind it. It has a name, which is the string that represents it when it prints. But it can also have a value, if it's a global variable or a local variable. And it can have a function bound to it. It can have a property list, a whole list of keys and values. The point is, you can have the same symbol, which has a property list, a class definition, a function, and a value, and they don't clash or collide with each other. So the fact that there's a function in Lisp called list, where if I say list 1, 2, that produces a new list of 1, 2, I can still have a variable named list, and it won't collide with this. I don't have to come up with a contrived name like LST for my variable. You can still have a local variable, even a global variable called list, with no collision. So symbols can be tested for equality with EQL, which is a lot more efficient than string equal compares all the individual characters in these strings. They're basically arrays of characters. So string equal checks if they're the same, but they're not actually the same address in memory. They're not the same identity of objects. Just checking if these two strings are made up of the same characters. But when you're checking two symbols, these symbols actually resolve to the same memory address all the way down. So these are truly equal. They're the same thing. They're the same identity. And lists, of course, are fundamental. So this is the thing that really distinguishes a Lisp dialect from some other languages that may look like they have a lot of the same features and characteristics. The programs are lists. So any Lisp program fits all the characteristics of a list formally. So that makes it easy for Lisp programs to generate and execute other Lisp programs. That's what GDL is, just a big Lisp program that generates other Lisp code. And most languages don't have this, what they call homoiconicity, I think is the word, where the fundamental data structure in the language is also the format of the programs in the language. Just look at the shape of it, convince yourself that this meets the qualification of a list. There's a parenthesis, a symbol, another list, and then another list with a symbol, a string. So then that's a little Lisp program, right? That can go at the top level just like any other expression, and it returns the name of the symbol that now names that function, which has this body right here. Now, using the list function evaluates all arguments. So this one will evaluate anything that's not quoted inside of it. So we can prove this to ourselves real quickly. Some really old ancient code, you may see the word car instead of first. That's a synonym, and that's real low-level stuff. It stands for contents of address register, but we use first. So first is the first element, the second element, the third element. Rest is everything but the first, and that's useful for a lot of recursive operations where you want to do some operation on the first and then a similar operation on the rest recursively. Nth allows you to index your way into a list. Now, if you have a long list, then using nth to pull things out of it is not the most efficient way to do things, because nth does have to walk the whole list in memory, one cell after another. So there are arrays and hash tables and things for when you get into those kind of structures. But GDL tries to make most of those fancy data structures not always so necessary if you just stay with the framework. Nil has a couple roles. It's an empty list. It's also a symbol. So it's both an atom and a list. That's one symbol that's a little bit special because it's an atom and it's also a list because it is the empty list. If you enter nil, it comes back as nil. The symbol nil, quoted, is also nil. An empty list is also nil. And a quoted empty list is nil. These things all evaluate to nil. So nil plays a couple of different roles. And it also plays the role of falsehood. When we start to get into conditionals with if expressions, for example, or anything that returns nil is considered false. Anything other than nil is true. Now, testing for listness just tells you T or nil if the thing is a list. Based on what we just talked about, what do you guys think this is going to return? Is that going to be T or nil? Yeah, qualifies as a list. For a normal Lisp function, we use defun, which is a special form. It's actually a macro. So defun does not immediately evaluate its arguments. It just assigns this function body to this name. And that means define a function named heyNow, which takes no arguments, which does this, prints heyNow. So it basically does a side effect. This one doesn't do a side effect, but it returns a value. So in Lisp functions, there's no explicit need to use the word return. It's just whatever the last expression is within the body will be the return value. So if I define a square and then call the function, just with the normal syntax, and it's telling me here it takes x, maybe more descriptive if we use a more descriptive name for the argument in here. So now when I call square, it tells me num, okay, at least gives you a hint that it takes a number. So that simply returns a value. There's no side effect, and that's typical. No side effect going on, it just returns whatever's the last thing in the. It's important to use some kind of editor that at least can do the indenting and at least can do the parenthesis matching. And most of them can these days. Pretty much any editor you pick up will have a mode that can do this much, I think. But any kind of programming editor should be able to handle this. These things are unreadable if they're not indented properly. So when you're reading code, you read it based on the indentation, and don't try to match parentheses with your eyes. You pretty much can let the parentheses fade away when you're reading the code and just look at the shape. And we also don't really have a need to dangle parentheses like that. Rarely is there a reason not to simply stack up closing parentheses like that on a line, because you're not trying to manually match these things anyway. So local variables are bound with let. They're bound in parallel conceptually, so the second one can't depend on the first one.